Without a reticle, a riflescope is just a useless telescope attached to your rifle. A glorified spotting scope, if you will. Reticles give the ability to find a fine aiming point on your target and actually point the rifle in the right direction. And for 200 years, hairs and spider silk were amongst the weird and wonderful things that we used to make simple crosshairs. But things have evolved so much. We now have incredibly complicated, incredibly precise reticle designs with all kinds of floating features. And today we're going to get into it. What is a reticle? What are the different ways of making a reticle? Where is it located in the riflescope? And how do we actually illuminate them? Let's first get into the what and where. A reticle is not something that you can just push a button and laser engrave into the scope. It's a very, very specialized physical part that has to be made in a very precise way in a specialized factory and then installed in the riflescope. As for the where, a reticle can be found in two locations. In the first focal plane, which is right between the turrets at the front of the erector tube, or in the second focal plane, which is at the rear of the erector tube beneath the magnification ring. It can also be found in both in the case of a dual focal plane riflescope, but those are far less common. A reticle in the first focal plane will be tied to the image coming in from the objective, meaning that when you zoom in and out, your zoom system is going to magnify both at the same time, and the reticle will appear to zoom in and out with the image. Reticles on the second focal plane are behind the zoom lenses, so the zoom lenses are magnifying the image in front of them, but the reticle is only being added to the equation afterwards, so it maintains its apparent size at all times. So as far as the physical properties of the reticle itself, there's actually no difference between a first and second focal plane reticle. What makes it first or second focal plane is where it's physically located in the riflescope. And there are pros and cons to both, but that's a topic for a totally different video. For now, we're more talking about what it is. There are two main ways that reticles can be made nowadays, and each has its pros and cons. But to start off, we'll talk about the first one, the wire reticle. A wire reticle is what is commonly used in simple second focal plane designs that don't have any floating features, like, for example, our Raptor 1F reticle in the Helix HD Compact. A wire reticle is made by physically cutting out the reticle shape from a piece of metal and suspending it inside a circular frame. This works really well if the reticle thickness is reasonable and the entire reticle is connected, but because no part of the reticle can be disconnected from the frame, floating dots, numbers, etc. are all out of the question. The two main advantages of this design is that they are generally more affordable, and they also allow for a type of illumination called fiber optic illumination, which we'll get to a bit later, which is really desirable for some use cases. The main disadvantage that people might mention is that wire reticles have a reputation for not holding up against extreme shock. However, that's not really a big factor anymore with modern designs that go through very, very strenuous shock testing and are made to hold up, at least from our supply that we use at Element. The next reticle type we'll discuss is an etched reticle, which is what we use in most of our riflescopes. An etched reticle is basically a disc of glass that has the reticle design etched into it and then filled with a non-reflective material. Etched reticles have a number of strengths. One of them is that they can be made extremely precisely with very, very fine features. This is particularly important with first focal plane reticles that have a large zoom range, because essentially you're zooming in on the reticle features, so they're going to need to be very, very fine so that at maximum zoom they don't just blow out of proportion. The size and shape of the reticle features have no effect on the strength of the reticle, so this opens the possibility for floating center dots, Christmas trees, etc. The main downside of an etched reticle is that they're generally quite expensive to make, but a secondary issue is that they often can't be made bright enough when trying to illuminate them for certain use cases. And talking about illumination, how does that work? Riflescopes with illumination capabilities often have some sort of external control. This can be in the form of a dial located on the left of the body tube or on the eyepiece, and can also be in the form of a button. These control units will have a small circuit board that controls the output brightness and maybe some extra features like shake to wake, for example, and normally use a flat battery cell like a CR2032. A small wire will then be run to the emitter, which is found at the reticle itself and normally emits a red, green or orange light. As for how the reticle itself is illuminated, well, once again, there are various technologies available here. On an etched reticle, what we do is we actually fill a portion of the reticle with a reflective powder like titanium dioxide, for example, and when the emitter shines on that area, the light gets reflected off and scattered, and some of that light reaches your eye, making the reticle appear like it's lit up. The benefit of this design is that you have complete control over which portions of the reticle you want to be illuminated. However, the downside is that there's a limit to how bright this can be made before the light begins to bleed and leak. It's also harder to illuminate small points like a little center dot that need to be bright. The light from the LED emitter may be really bright, but when it's reflected off that reticle surface, it gets scattered and only a tiny portion of that light actually makes it to your eye. This is where fiber optic illumination comes in. Fiber optic illumination is the better solution for obtaining a very bright, very fine aim point with no light leaks. This can only be done on a fiber reticle because a physical fiber optic strand has to be run up behind the reticle crosshair and exit right in the center of the reticle or wherever you want your illumination point to be, from where it can be directed straight towards the shooter's eye so that the entirety of that light travels straight and doesn't get scattered. And that's why this can be so finely controlled and be made so bright. But obviously the issue is this can't be used on an etched reticle. So what is the solution for an etched reticle? Well, there is a new technology called diffraction grating, which we can run over briefly. It's much harder to explain how this works, but basically it allows for complicated floating reticle designs, but instead of relying on light being scattered off the reticle surface, it relies on diffraction, which is a much more controlled way of getting that light directly to your eye. Think of it like a torch being adjusted. The actual amount of lumens being output by the torch can be the same, but when that torch is narrowed and it's pointing directly towards you, it makes it look much brighter. And that's the idea behind this technology. So it works really well on something like an LPVO or MPVO that requires it to be used in very bright conditions at very low zoom where the reticle features are really, really small. That's where it kind of shines, no pun intended. Lastly, I should mention that reticle features have to be so finely calibrated and made to actually line up with objects downrange like they should. So for example, if your reticle subtensions have 0.1 milliradian hash marks, that's got to fit within the space of 1 centimeter at 100 meters perfectly. And to me, that's one of the most impressive aspects of a rifle scope, that precision of manufacture. If you enjoyed this video and want to learn more, you can subscribe to follow along on the series, or you can visit our website at element-optics.com. Thanks for watching.